Hello friends, today's question. A disk is rolling without slipping on a horizontal surface. C is the center, Q and P are 2 points equidistant from C. Let VP, VQ and VC be the magnitude of velocities at point P, Q and C respectively. Then we have to prove one of the options. So this is a disk which is rolling without slipping. Let us suppose it is rolling with the angular velocity of omega, and the point of contact of the disk, let us suppose that is called as A. Okay. So we usually frequently use a relationship in which the center of mass is related with the angular velocity in terms of the radius, and that is calculated based on this point of contact. Okay. So for this, let us suppose we have, this is a circular disk or any circular object which is moving, and A is the point of contact, is a center of mass, and this, the center of mass is having a velocity of VCM, and then this point A is going to have a velocity that will be in the opposite direction, and it is moving with the angular velocity omega, so that we can write as minus r omega I, where r is the radius of it. Therefore we can write the relationship that velocity of point A, that is given as Vp, will be equal to minus r omega I, and this will be plus I rather, and this will plus VCM I. And in the pure rolling condition, the point of contact velocity is always equal to 0. We can say for pure rolling, Vp is equal to 0. So from here we can say the velocity of center of mass is equal to r multiplied by the angular velocity, so where r is this radius. So it means the velocity of center of mass is the product of the radius, or rather we can say perpendicular distance. In this case it is radius and the angular velocity. So in case this is specifically for the center of mass. Similarly, we can calculate for any point in the circular disk. Therefore, let me draw the figure again, the given figure rather. So this is our point of contact A. We have C, point of center of mass, a point Q, and we have point P. And we already calculated. Let us join C and A such that, and it is going to have a velocity which is given as Vc. So therefore, and forgot to mention the angular velocity, so we can say the angular velocity or velocity for point C, which is given as Vc, will be equal to omega multiplied by the distance Ca. Let us call that as RCA. And for point P, or rather let us start for Q, we are simply going to join this QA like this and draw a velocity vector which will be perpendicular to this point Q and which will be going something in this direction. So this will be our VQ. Therefore we can write that velocity for point Q, which is given as VQ, will be equal to omega multiplied by the distance QA, let us say that is R QA. And similarly, we have point P, and let us join this point P and draw the velocity vector which will be perpendicular to this. So it will be in this direction, which will be our VP. Therefore, we can write that velocity for point P, and that will be governed by the equation that Vp is equal to omega multiplied by the distance RPA. So we have these three equations, and using three equations now we can simply find out their respective relationship. So let me draw this. So from here we can clearly see that our RQA is greater than RCA is greater than RPA. So we can substitute the value. We get RQA is VQ upon omega is greater than RCA is VC upon omega, and this will be greater than VP upon omega. Therefore, we get the final answer, which will be VQ is greater than VC is greater than VP. So the option number A is the correct option. You can say option A is correct option. So herein one important thing is that the velocity of the center of mass or any point will be calculated with respect to the point of contact, and the point of contact velocity is always equal to 0 for a pure rolling motion. So this will be giving us these three equations, and then we can simply say with respect to distance, because herein it is specifically mentioned that point P and Q are equidistant from C. So on the basis of this we can just solve it. Okay. So this completes the question. Thank you.